Okay, it's working. Okay. Hello, everybody. So welcome to Chem 3510, Intermediate in Organic Chemistry. And so you will see the course content uh, in the course syllabus, which is provided in the course canvas. Okay. So I'm going to give you a basic concept or the basic theme for uh, the subject of inorganic chemistry. Okay, so inorganic chemistry, we're dealing all elements in the periodic table, including carbon, hydrogen, or of course, entire periodic table. Okay, and the goal of the task of the subject is to study the elements and the compound based on different elements, and to study how we make them, how we purify them, and study their physical properties like, magnetic property, and also redox properties and reactivities, something like that. Okay. And another thing is important task is we need to understand the structure of your, compound. Regard, uh, it doesn't matter the compound, what elements form this compound. Okay, and then another important thing is applications of the metal ions and metal complex in the field of inorganic. So, for example, we can use inorganic solid as magnetic materials or as electronic materials. And in many cases, we use them as um, catalysts or even we can use metal compound as medicine. Okay, believe a lot. Okay. So this class, the first class, I'm going to show you some uh, basic structure and bonding principle about inorganic compound. Okay, from simple one to relative complex one. Okay, so the first one I'm going to emphasize is about octet rule. Okay, um, I believe all of you have taken general chemistry, or maybe some of you have taken a class of organic chemistry. You should know octet rules, right? So octet rule means you want to have 18 electron surrounding a central atom. Okay, central atom. Okay, normally in octet rule we use new structure to describe the electronic structure of a simple compound based on the octet rule. Okay, so the reason is why octet rule, because especially for the simple inorganic compound, no matter carbon based centered or nitrogen centered, so if it's surrounded with 8 electrons, so it means it form a stable electronic structure. Okay, so because stable, right? It's stable. That's most of compound that tends to form this rule uh, to have 8 electron around the central atom to form a stable ion or stable compound. Okay, so then as I said, we use Lewis structure to show the electronic structure of a compound. Okay, so the thing is, uh, we deal with the valence electron. Valence is means the electron in the most outside sphere. So we will show that. We will give you example with them going. Don't worry about too much. Okay. So in this octet rule, we only consider valence electron to form when we draw the new structure. Okay, draw the new structure. So another thing is we need to choose central atom. Okay, central atom. So central atom, when we choose central atom, always in pretty much the central atom is most electron positive. That means the central atom is in most cases is positive charge. It tends to lose electron to the surrounding atoms. Okay, so that's how you choose central atom. Okay, And then when we draw the new structure for compound is, if there's a bonding, okay, if there's a bond between central atom and non-central atom, then we use a dash, a short line to represent that a bonding pair, okay, bonding pair, okay. So then you will say there are also additional valence electron in the central atom or non-central atom. They do not form bond. Okay. Then for these electrons, uh, if they are paired, we call them non-pair, and we use dot, a pair with dot, or even something you can say single dot. Okay, but we use dot to express, to describe the non-bonding electrons. Okay, non-bonding electrons. Okay, that's a basic three basic rule when you draw a new structure for a compound. Okay, okay. Then let's give you example. Okay, okay. In this case, let's write the new structure for BF4. Okay, BF4. And so, can anyone tell me how many valence electron we need to consider for boron? Think about the, if you have a periodical table around, you can check it. And so how many valence electron we should consider for boron? How many valence electron we should consider for fluorine?
It should be 3 for boron and 7 for fluorine.
Okay, I think you are right. And I will take a pen because you answer my question. You get 0.5 credit. Okay. Okay. Let's get a pen. So your name is, can I see your name?
Joel Ashton.
Why I don't see your name? Let's see. How about after class, you just come back to me, make sure, okay, at the end of class. So if you answer question or if you ask question, you can report back to me. Okay. Okay. I just save the time for the moment. Okay. So here is a new structure. Okay. New structure for the, for this BR4 anion. Okay. So as Josh said, we consider, we have three, valence electron. Okay, three valence electron. Okay, let's see. Let me double check. Okay. So right now we have boron with 3 electron, right? So think about octet rule. So you only have, you know, uh, 3 electron from boron, right? From boron. Then what you're going to do, you need how many electron addition to have 8 electron around boron? You need additional 5 electrons, right? Does that make sense, right? So let's consider, so for, because if boron has 3 electron itself, and it will form 3 bond with 3 fluoride, then you have 3, bonding pairs here, right? And then you get 6 electron. Then what additional what you're going to have is, you want to have additional pair from a fluoride anion. So then you can form a fourth, okay, a fourth bond pair here, okay. Then if you look at the fluoride fluoride ion, okay, fluoride ion. So what you're going to have is, so because that's anion, fluoride here is anion, okay. So what you are going to have is uh, this one fluoride anion here, okay. So what you are going to have is going to, for each fluoride, you are going to have additional three non-pairs, and we draw them as a pair of dots on each side, one pair, second pair, three pair. So same thing for other three fluoride, right? So then you are going to have this, anion. So if you look at the chart here is boron here is plus three charge. Okay, because it's a central atom, it tends to lose electrons, right? So in terms of the oxidation state, so we treat boron as plus three. And for each fluoride, they are minus one charge. So overall, you get minus one charge for this BF4 anion. Okay, does that make sense? Okay. And here, that's the actual geometry of this BF4 anion. Okay, BF4 anion. Okay, that's a typical tetrahedral anion. Okay, tetrahedral anion. Okay. Then in this slide, you can see I give you additional examples of the new structure for simple compound. The hydrogen is simple because each hydrogen only have one electron, right? So two hydrogen, when they come together, they form one hydrogen bond here. You only see one dash. You don't see additional dot because hydrogen does not have additional electrons, right? So each hydrogen only has one electron. So it from one bond here. So here it's just two electron. That's a not octet rule because that's a two electron rule. That's a special case for hydrogen. Okay, because it hydrogen does not have electron to form octet rule. Okay, but if we go to dinitrogen, this compound, this dinitrogen molecule, right? So you can say how many electron we consider as a valence electron for each nitrogen. Who want to get 0.5 credit point?
5.
Yeah, great. And then report back to me, you get 0.5 point, okay, at the end of class. So then you think about, you have 5 electrons, right, for each nitrogen. Based on follow the octet rule, that means it needs 3 additional electrons to, it goes up to 8 electron for each nitrogen, right? Does that make sense? Then in this, that means, so you are going to have 3 paired bonding between 2 nitrogens, okay? Right? Then each nitrogen will have how many electrons? 8 electrons, octet rule, right? Then it form a stable electron structure on each nitrogen, right? Then for each nitrogen, because since it's only use 3 electrons to form 3 paired bonds, 3 bonding pairs, right? Then each nitrogen left 1 non-pair. So on each side, you will say a pair of dot on each side of nitrogen. So that's a new structure for dinitrogen compound, okay? Everybody got that? Okay, let's give you a little bit more complicated. So in this case, so for we call it homoleptic compound, we treat them as 0 charge because they are same thing. They share electrons. So in your chemistry, we treat, in this case, if the homoleptic compound, like dinitrogen or dioxygen, the oxidation of this element, they're always 0, okay? Because they share electrons. No polarization between atoms. But in this case, in this carbonyl oxide, so we are going to have something different, okay? Then what we are going to have is, we will have, the carbon as positive charge, and carbon monoxide as the oxygen as negative charge, okay? So then what you can say is here carbon is +3, oxygen is -3, okay? Because carbon tends to lose electron, okay? Okay. Let's give you one more example, okay? Like the this one, okay? That's a sulfate. That's an anion for sulfuric acid, right? Sulfuric acid. Then how many electron valence we consider for sulfur? Someone else?
6.
Who said that? John?
John.
Okay,
Yep.
6, right? Then how many electron we consider for oxygen? I hope a female student can answer this question.
6.
Who?
Me, Adam Rasmussen.
Yeah, oxygen. How many?
6.
Okay, yeah, you are right. So because they are in the same, they are group 6. Yeah, they are in the same group, right? Remember, if you have a periodic table, oxygen, sulfur, right? So they are in the same group. They both have 6 valence electron. So then the same rule, okay, same rule, okay. And let's say let's see, in this case, okay, let's talk about oxygen. Oxygen is easier, okay. Oxygen, you say for each oxygen, since it has you know uh 6 electron, right? It just need a additional 1 pair to form what? To form octahedral electronic structure, right? So you can say, so for these 2 oxygen here, so they only have 1 bond, that's enough. Then they left over 3 non-pairs. Then for this oxygen and this oxygen, each of them have 8 electrons, right? Does that make sense? Right? And for the bottom oxygen and the top oxygen, they also have 8 electrons. The deal is they form 2 bonds with sulfur, and then each of them has 2 lone pairs. They still hold 8 electrons, right? Then you may wonder, how about sulfur? What's wrong with sulfur? Can someone tell me?
It's
It
got
has
more
10
than 8
electrons.
electrons.
Yes, you catch it. You catch it. Okay, that's good. So the reason is so when sulfur when you go to the second row, when you move on from the, because we treat the oxygen row as a first row, right? The yeah, that's a let me no, yeah, oxygen is second row. So when you move to larger atom like sulfur, third row element, so they tend to have, in some cases, not all cases, okay, in some cases they tend to have, we call that hypervalence. In another way, they tend to violate 8-octet rule, okay. And then you can say in this case, sulfur has how many valence electron? 1, 2, 3. How many? 8. They have 12. It has 12 valence electron. If you do counting, right? So that's what we call hypervalence in this case. But if you move back to this case, SO3 molecule here, right now sulfur still hold, what I'm trying to say is still, hold the phono octet rule, okay? Octet rule. The reason is in this case, like also this case, perchloride anion. So the reason is because when they have more, more than 3 negative oxygen around, so what's going to happen is, all these 6 electrons vanished from sulfur, they tend to share with oxygen. So they form, in this case, you can say it forms 6 bonding with 4 oxygen. Does that make sense? So that's what I'm trying to say is, octet rule is general rule, but when you move to third row and central atom, it tends to have hypervalence electronic structure. Okay, so that's kind of exception. Okay. So far so good. Okay, good. Yeah, you guys can stop me to ask any question at any point. Okay. Yeah, let's check my time. Make sure I don't want to.
I had a question for you.
Uh-huh.
So, do we need to memorize all of those different elements that would tend to be have hypervalence
So no, you
forms?
don't have
Or
to. The reason is what I'm trying to. So if I give you SO4, right, for example,
yeah,
right. So the first thing you can do is you draw, you know, non-central atom around central atom, right? So you first you do is you try to make non-central atom to form octet rule,
okay,
right? Then what you can do is, if needed, you can maximize the bonding pair, but the bonding numbers for the central atom. You get my
okay,
point? Yeah,
yep, that sounds good. Thank you.
yeah. That's kind of the how the kind of that's a way you deal hypervalence compound or ions. Okay, so
Okay,
you in any case, in all these cases, non-central atom like here, all this oxygen, they always follow octet rules. And then for the sulfur chloride here, and you just draw bonding, the bonding number of bonding pairs as much as needed as you can. Does that make sense? Okay. Okay. That's then
Okay, I
here
have a
I'm going
question.
to tell you a little concept called resonance. Okay, so resonance is it's kind of the uh, you know dynamic electron structure for same compound by shifting the pair, bonding pair and lone pair, the distribution of bonding pair and lone pair surrounding the non-central atom. Okay, so I'm going to show you uh, uh, how it works. So the deal is when the in reality is when the electrons moving around between central atom and non-central atom, it helps to stabilize the energy to make this compound or ion more stable. That's why we need to have this resonance phenomenon in reality. Okay. So for example, this BF4, okay, BF4, right? BF3, sorry, BF3. So that's a regular, Lewis structure we draw for BF3, right? But also, what you can do is you can draw, this type of, Lewis structure, right? So what you can see is, uh, when you shift, one more non-pair become a shared uh, electron between boron and fluoride. So you are going to have a BF double bond here, and you have BF two BF single bond, and you can do the same electron shifting. You can move the double bond uh, to the top fluoride, or move the double bond to the right side fluoride. So you can see then we have four different Lewis structures, and then they form resonance between four of them. Okay, this type of electron shifting, from fluoride shared with boron, and then you can have this non-pair shared with boron, or this non-pair shared with this boron, or from this non-pair shared with boron to form BF double here. So when you have this RAN structure, they tend to make this BF4 molecule more stable. Okay, more stable. That's the reason we have the RAN structure. Okay. Same idea here. So for this NO3 nitrate anion, so you can have this, you have in this one, you have three NO single bond, right? NO single bond. And then you can, same idea, you can share, move one non-pair from oxygen to form a bonding between nitrogen and oxygen. And you can have a NO double bond, okay? And NO double bond can be formed between, you know, uh, this oxygen, uh, this oxygen, or this oxygen. So then you have these four different new structure to form random structure for this NO3 anion. Okay, does that make sense? Okay, that's called the resonance structure. Okay, so the idea is when you have these different, electronic structures, electron distributions, you make the whole system, make this compound or anion more energy stable. More, to lower the energy, make them more stable. That's the whole reason. Okay. So another reason I'm trying to tell you is the electron distribution in the system is kind of dynamic. Dynamic. So, uh, for example, you can not only say in principle, okay, in principle. So you will say just for this BF3 molecule, it has these four different electrons coexist in the same time. Okay, what I'm trying to say, you cannot, in reality, you don't only uh, they're not only these BF3 single bond structure here. Okay, it also have other three structure coexist. They are also there. Okay, okay. So far so good, everybody. Any question? I'm gonna move on. Okay, okay, can move on. So move on. I'm gonna show you a new concept. It's also important principle for inorganic chemistry. It can be applied to simple compound and up to more complicated molecule structure. Okay, so that's what we call the Vesper model. So valence shell electron pair repulsion principle. Okay, repulsion principle. So so up to this point, I showed you how to use loose structure to draw the electron distribution for a molecule or for ions, right? Here, I'm going to show you how to use this principle, Vesper principle, to draw the geometry of a given compound or ion, okay? Given a compound or ion, okay? So in this case, in this model, okay, in this Vesper model, so we define the region of electron density, okay? So we use electron density to define a possible position, okay? So the electron density can be defined as a paired electron or non-paired electron, as we talk about in the new structure, okay? In new structure. So another principle is so in a given molecule, so each pair, no matter the lone pair, is paired, okay? It's for bonding or for non-bonding pair, okay? They always take a position in the geometry. And there's a second rule for this principle is lone pairs, okay? Lone pairs, they tend to be more electron repulsion than the paired electron, okay? Because non-paired, they have a higher degree of freedom. It can give a repulsion stronger than paired electrons. So I'm going to show you what I mean, okay? So for this, in this case, right? So in this case, so that's a that's a central atom here. It's bound with 4 non-central atom. So you can draw this. Let's call that X4 Y4. Okay, XY4. Okay, so you can draw this geometry. So if central atom has an additional non-pair here, okay, you can draw this geometry, or you can draw this. This we call seesaw geometry, or you can draw this, triangular pyramidal geometry, and you then based on this rule, non-pair has higher repulsion than the, bonding pairs. So in this case, so can someone tell me which one is more stable?
I think in this case, it'll be the seesaw geometry that's more stable. 'Cause it gives-
Why? Can you tell me why?
Yeah, so the lone pairs are going to have that, stronger repulsion. And so in the, trigonal planar model, they're not as far away. And so I think the seesaw is going to be.
Yeah, that's good. So what I'm trying to tell you, so that you basically you are right. So in the structure, in the geometry A, in this case, right? So you have lone pair, you put the lone pair in the equatorial plane. So the repulsion with lone pair only 2 pair bonding pairs, right? But in the second case, if you put the lone pair at the axial position in this geometry, then you are going to have 3 repulsion of paired bond with this lone pair. Then, based on this rule, so you have in this geometry, you have higher energy because you have additional, repulsion between lone pair and the paired bonding pair. So that makes this geometry is more stable. Okay, that's a trickier case. Okay, Then here, so that's the geometry we can draw based on Rush principle for PR5, phosphate pentachloride. Okay, so here you can say phosphine, right? Phosphine will have 5, valence electron, right? 5 electron. So it forms 5 bond for 5 chloride atoms around. Okay, so that's a 5 bond, right? 5 bond. So in order to minimize the repulsion between each, bonding pairs, then we are going to have this because right now we have 5 electron regions because we have 5 bonding pairs. Then we will have this trigonal bipyramidal geometry. Okay, so that's kind of the typical geometry you are going to have based on the number of electron regions, paired electrons or non-paired electrons. That's electron regions. Okay, and here is the BF3. Okay, BF3. Okay, BF3, you see it has 3 electron regions because we have 3 bonding pairs here. Okay, bonding pairs here. Then we are going to have this trigonal planar geometry. That's this case. Okay, this case. Okay, this case. So you can say we are going to have, different. I'm going geometries for different molecule or ions, right? So we have linear, bent, triangular planar, and also we have triangular square, pyramidal, octahedral. Okay, octahedral. Okay. So I hope you guys can, use this as a guidance or use this as guidance. You right now you only see this the geometry, describing text for this molecule or ions here, but I hope you can practice them, scratch paper. You draw them out. Why it's linear and why it's bent. Okay, why it's bent. Okay.
I have a question.
Okay.
On that slide here, with the square planar, could you draw out that molecule? Why would it be square planar instead of tetrahedral?
Oh, this one, right? Okay, that's good. I think I have example later a lot. I can draw it here right now. Okay, that's good. So you see, that's a we have 4 bond because the 4 fluoride with exon, right? Then think about reality. That's so another thing is, how many Venstern for exon?
8.
8, right? So it formed 4 bond with 4 fluoride. So it has additional what? It has 2 additional non-pairs there, right? Did everybody get it?
Yeah, that makes sense.
Right. So Okay, that's the right structure. Okay, I'm doing the right structure. So in this case, right? In this case, actually, how many electron regions we have here? 6 or 4? Who has a question?
Yeah, there's 6 electron regions.
Yeah. Okay. Oh, never mind. Let's. Oh, I should keep it anyway. So let me do it again. We have exon. It's a little bit ugly, but you understand what I'm trying to do, right? So we have fluoride. So we have 6 in the region here, right? Then, so when we talk about geometry for a compound, we only consider the distribution of the real atoms. So we omit the position for pairs, okay, for pairs. But the deal is that's actually as a pseudo octahedral compound because we have this 2 lone pair occupy the axial position in octahedral geometry, right? But the deal is what you can do is can you switch the position of fluoride under this lone pair? Who asked the question? I think who asked the question?
I did. So are you asking if the fluorine can switch places with?
Yeah, if you can you switch a position fluoride under this lone pair?
No.
Why?
Because the way that it's oriented right now with those fluorines in that plane, I think that it's maximizing like the distance between them and giving the lone pairs the most space.
Yeah, so basically right. So you want to minimize the repulsion involved lone pairs, right? In this case, if you put the 2 lone pairs opposite to each other, it has minimized repulsion between these lone pairs. If you switch fluoride with the lone pair, then what you are going to have is this 2 lone pair will have a 9-degree angle. You will have increased lone pair repulsion effect. Does that make sense? That's why we place 4 fluoride in the equatorial plane and 2 lone pair at axial position to minimize repulsion effect to make this geometry more stable. Does that make sense? So that's the most stable geometry for this exon tetrafluoro compound. Okay. So I think that's a good example. So you can follow this example. We can try to practice with other ones. Okay, square pyramidal, triangular pyramidal. Okay. If we have time, we can do more practice. Okay, at the end of class. Okay. And also we can come back even at the beginning of the next class for more example, okay? More example. Let's draw water, okay? Let's draw water, okay? Okay, so that's oxygen, right? Then we're gonna have two oxygen hydrogen bond, right? Then how many lone pair we left with oxygen?
2.
2 lone pairs, right? So in fact, you will see, because this molecule, because you need to imagine it a bit. The real geometry of this water molecule, if you consider the electron region of this 2 lone pair, it's a pseudo tetrahedral, okay? But if you look at the geometry of the real atom, oxygen to hydrogen, that's a bending structure. Okay? Got it? So Yeah, we already have the draw structure for BF3. Okay, BF3. Okay, and this is easy. Tetrahedra is easy. Okay, and yeah, remember. So the SF4. Think about this. This one is a tricky one, but we talk about SF4. Okay, so SF4 is actually that's the case for SF4. Okay, think about so what's its geometry for SF4? Okay, remember this slide. You can practice. What I will ask someone to show me this the geometry for the SF4. Okay. All right. So I think I'm going to uh, quickly introduce the Wencesman's theory. I think that's the last topic for this class. So Venn theory is just it's a um, quantum mechanic theory to deal with binding interaction between atoms within a compound or ions. Okay, so the basic rule is the Venn theory is consider the you know the interactions of atomic orbitals of each atom, central atom or non-central atom. Okay, when they form bring together, the orbital atomic orbital of each atom, they will interact with each other to form bonding. Okay, form bonding. Okay. So here is atomic orbitals. We have okay at the different levels. So that's the s orbital. That's a spherical shape, and that's a p, px p. I think most of you love that. I just do a quick review, and that's a px py pz. Okay, and that's the polarized atomic orbitals, and along x we have px, along y we have along z we have pz py. Okay, and also we have 5d orbitals, atomic orbital. They have different shapes. Okay, different shapes, and for f orbital we have 7 shapes. But for this class, even for up to graduate school, you just need to memorize the the shapes, atomic shapes of s orbital, p orbital, and the 5d orbitals. Don't worry about f orbital. Even I'm showing here, but we are not we're not testing. Okay, at least. But for the shape of s orbital and p orbitals and d orbital, you need to memorize the shapes. Okay, that's a point. Okay. So let's look at the hydrogen atom. Okay, let's look at the hydrogen atoms. Okay, hydrogen molecule. Okay, hydrogen molecule. So the basic idea is when you bring these two hydrogen together, and the S shape. So each side has S shape atomic orbitals. So they will overlap. Okay, they will overlap, and then when they overlap, they will overlap the region here. Okay, so this region has a higher electron density. So because the density electron is negative charge, right? The nuclei of hydrogen atom, they are positive charged. When you have increased electron density between these two, then this overlapping density has a rule to bond these two nuclei together. So that's in physical, the meaning of physics. That means this overlapping density, through electron attraction to bring these two hydrogen atom together. That's why we have a bonding orbital here. Okay, because this increase in electron density, have a higher, electron, charge electron, charge attraction between, to hold these two hydrogen atom together. Okay, these two hydrogen atom together. Okay, but you don't worry about this figure. But the basic idea is when you move when you move the play the distance between these two hydrogen atoms, so you will see the how energy change of this molecule. Okay, when you too close, when you say it's too close, you have relative high energy. That's the reason. Because why? Because the reason is your the repulsion. Okay, repulsion between the nuclear positive charge makes the molecule not stable, and you have to increase distance to make sure you have the highest attraction energy of this overlapping density with the nuclei. But however, when you increase the distance between these two hydrogen atoms, you also increase the energy, because you lose the overlapping density between them. Okay, so that's the profile of the energy change with the distance between the two hydrogen atom. Okay, two hydrogen atom. Okay. So in this case, when you have the overlap with two s orbital shape, so we call the sigma bond, because that's head to head. So that's head to head overlap. We call that sigma bond. And you can imagine you can also have head to head overlap with p orbitals. Okay, with p orbitals. Okay, so we will see example later. Okay, we have head to head with p orbitals. That's also sigma bond. Okay. So when you have the overlap between p orbital from side to side, so we call that pi bonding, because that's side to side. Okay. Normally we have head-to-head overlap. It have a stronger overlap, and that's what I'm trying to say. Sigma bond, in principle, has stronger and bonding energy than pi bonding. Okay. Okay. So because that's a more overlap, so you'll have more overlap in the density there. Okay. So pi bonding overlap in the density is smaller. Okay. So make the attraction effect is smaller with nuclei. Okay. And here is a bonding, the how do you say, the orbital overlap for the dinitrogen molecule. Okay, dinitrogen molecule. So remember, dinitrogen has 3 bonds, right? So if 2 lone pairs on 1 lone pair on each nitrogen, but they show 3 bonding pairs. Remember? So that's in the one of the early slides we showed the new structure, right? So for one of them, it's head-to-head. Okay, one of them is head-to-head bonding. So that's one sigma bond, and other 2 p orbital from each one, they form side-to-side overlap to form 2 pi bonding. So for 3 bonding of dinitrogen molecule, 1 is sigma bond, that's px head-to-head bonding, and py and pz, they are side-to-side overlap and to form 2 pi bonding. Okay, 1 sigma bond, 2 pi bond for dinitrogen molecule. Okay, that's for this example. Okay, and here is oxygen. Okay, water molecule. Okay, then we have 3 atoms here. So you have 2 head-to-head sigma bond between oxygen and hydrogen. 1 here, 1 here. They are sigma bond. Okay, they are sigma bond. Okay. So there's another concept called the hybridization. So what does that mean is, so when you have different bonding with the central atom depends on the number of the we also call the coordination number or bonding numbers along the central atom, then you are going to have different geometry. And the reason you have different geometry because the SP of the hybridization and P of the D of the hybridization. So because this hybridization, so you can give the central atom to form, to allow central atom to have particular geometry to host the non-central atoms. Okay, non-central atoms. Okay, let's give you example. Okay, so you don't have to. I hope you can, you don't have to memorize this table, but at least you need to understand what's sp2, and sp3 hybridization. So I'm going to show you the example here, okay? So let's use water molecule as example, okay? So think about the atomic orbital around oxygen. So we have px, py, pz, right? So they are perpendicular to each other. Remember, right? However, so when it form the bonding with two hydrogen atoms, so you can say this right now the four orbitals, valence orbital around oxygen, is not the ideal shape, right? So that's because we have sp3 hybridization between one s orbital and three p orbitals. Then you think about that sp3 hybridization will rearrange the atomic orbitals of oxygen into a tetrahedral shape. Okay, tetrahedral shape. Okay, and in this tetrahedral shape, two sp3 orbital will form single bond with hydrogen, and two additional sp3 hybrid orbital will host two lone pairs. And then in this geometry, in this pseudo tetrahedral geometry, you will have lowest energy. Okay, if you want, for example, if you don't have this hybridization, then you use p orbital, two p orbital from the like this case, this that's a simple case. You just use the two p orbital to form symbol with the hydrogen. The problem is you are going to left lone pair in the perpendicular position to have stronger repulsion effect. Okay, that's the reason in this case we are going to have the sp3 hybridization first for the 1s orbital and 3p orbital for the oxygen single atom, and then to have this tetrahedral geometry, then we use them to bond with to have single bonding with two hydrogen atom to form this pseudo tetrahedral geometry. But if you forget the lone pairs, then you have this bending shape for this hydrogen water molecule. Okay, for this water molecule. Okay. So I'm going to stop here, but think about how can we draw geometry for these two examples, phosphine pentachloride and the sulfur hexafluoride. Okay, and then think what's the shape of this one? Okay, think about the shape. Yeah, just think about the shape. Okay, think about shape, and also think about the hybridization of the single atom. Use the table here. Okay, that's a quick homework, not official homework, but that's kind of a left question for the beginning of next class. Okay, okay. Okay, I'm gonna stop here. So anyone have any questions?
Will we be having a quiz next class?
No, you look at the, you can, that's a good question. You can look at the, let's